Welcome back. Hope you had a good break and we're ready to get started. For some of you it's the second semester, for others of you it's the third semester, maybe even a fourth semester for some of you, but we won't go into that. But I got a bunch of things to get us started and kind of go through the class in terms of the syllabus and what's expected. Why don't I start there? And it looks like I've got two syllabi here. Let me make sure I don't give you the physics. Okay, here's 123. And so we'll start with that, and I'll give you a chance for me to kind of introduce the class. And I'll go kind of quickly because you'll see it's a lot the same as the stuff you've seen before. The first homework assignment, I'll send that around. There's like before, and I'll talk more about that. Bookmark that has where the solutions are posted, and so everything really kind of the same that you saw already in Physics 121. And for that matter, Physics 122, although 122 is a little bit different. And I'll start by just turning on the web page here, or so I think I will. Good. And pulling up the syllabus that's online, partly so we can go through it, and partly also so that the web page in case you get it lost for whatever reason here. But here's obviously the City College web page. Here is the college departments. Here's academic department. Going down for physics, clicking on physics, finally getting to the place where it says entering the physics website. This is the part that we as a department can control. And then finally clicking on my web page and finally scrolling down to this class, Physics 123. I'll start there. Oh, no, I won't start there. I forgot to load the, put it on the server and copy it over to the server. That says spring of 13. Bummer. All right, so I will do it this way. I will do it from the sheet of paper. There's not much changes, and so maybe I'll kind of refer to this, but there are a few changes, so let me not take it too directly. But I think you know the first part, my name, my office hours. Those are a little different than last year because of the new structure, and I think some of you realize this. If not, I'll say it. This is the first time we've ever done Physics 123 with two sections. And so, as you guys know, some of you are signed up here at the 8 o'clock. We've never done a class this early at 8 o'clock. And then the other half of you are going to be at 10:30, 10:35, but I guess I got to figure that out too. But we go from 8 to 10:05, and of course that makes us the ability to have a fourth lab section. So some of you are going to have a lab tomorrow morning with Dawn, some of you have a midday with me, some of you have in the afternoon with me, and some of you will have it Thursday afternoon with me. So that's a little bit different, but here's what I really wanted to point out. In Physics 123, what is this class? And how is it different from the other physics courses? I'll start off with what is clearly the same right there. Very analytical. So yes, we are going to learn the physics, and yes, we are going to dive deeply into the math, just like you saw in Physics 121. So I would even think that this class I would call easier than 121. I guess we'll wait till the end and ask you what you think of it. But the reason I say that is I think there's a big learning that goes on in your first semester of taking physics, learning how to study the physics, learning the idea that it's about the basic principles and the deductive reasoning, not memorization and regurgitation of the information. And when you kind of learn that skill after you go through Physics 121, then I think it makes the next classes, 122 and 123, easier in that sense, although our material we cover tends to be a little bit more challenging, at least in 122. And I say that because that leads into, well, what materials do we cover here? And you can see it says mechanical waves, heat, light, and some modern physics. Let me pause for a moment and grab your book here. If you've got a chance to look ahead this semester, you will have noticed something. If not, let me show it to you now. Here is your book, and here are the chapters covered in the book, and we cover the book in 3 semesters. And so all of you know that either last semester or the semester before, depending on when you had Physics 121, we covered Part 1, Mechanics. And it was chapters 1 through 14. And so all of you have already done chapters 1 through 14. Then we start to talk about the other topics in physics. And part 2 is where we begin today. And this is what Physics 123 is about. Chapter 15, we start where we left off on 14. And so it is a short 4 chapters. That's it. It starts off with oscillation and mechanical waves. Then, I would call this part 3, we get into thermodynamics for 4 chapters. Then if you look at the book, you'll see that part 4 is a huge section. That's what Physics 122 is all about. So half of you took 122 last semester, half of you will take it next fall. But this part 4, we will skip over and then go into part 5 of the book, which is again 4 more chapters, and it's on optics. And then we get into modern physics, which this book is not the one with modern physics. And I hope the one you bought way back in Physics 121 says with modern physics, because it doesn't have it here. So I'll carry this one around until we get to the end of the semester, and then I will switch over to my heavier one and have the other chapters there. But here's what I'm trying to point out. Different than you guys saw in either Physics 121 or for the other half of you who had 122, it is not just one topic of physics that just gets deeper and deeper and deeper. Mechanics, that's what we did. We started in chapter 1, we learned a little bit about kinematics. Then we went into Newton's laws of motion, then we went into the conservational principles, and we just kept learning more and more and getting more advanced and more complicated problems. This class is a little different from that, and I want to make sure I make that clear from the beginning. Physics 123 picks up all the smaller sections, whereas Physics 121 is all about mechanics. Physics 122 is all about electric fields and magnetic fields. This class covers really the 4 other sections, starting here with mechanical waves and oscillations, going into thermodynamics, going into optics, going into modern physics. So it's kind of like a description of this class is 4 mini classes put together. And that's good and bad. The good part might be if we are doing a topic you don't like or you're finding challenging, we're going to leave it soon. We're only going to do 4 chapters and then move on. You might say also a good part is the problems won't get nearly as complicated and sophisticated as they did in 121 or 122, because about the time we really get to some good stuff, we leave. And we say, well, sorry, you'll have to do that next year when you transfer to the 4-year school and you take your advanced thermodynamics or you take your advanced optics or wherever your education takes you. And so that is a little bit different. And that's the bummer part for me, especially in thermodynamics. We get to some really, really good stuff. And then we're done. Like, oh, we're just right to the whole crutch of it. But on the flip side of that, I do think it's the best overall way to present the topics of physics and to present your education, where we give you these 4 chapters, say in thermodynamics, and then you pick up with that when you in your next class. And I think almost everybody in here will have to take an advanced thermodynamics. Only a few of you will probably have to take an advanced optics. And so the optics you get in here, for many of you, that'll be all the education of optics, formal education of optics that you get. Whereas thermodynamics, that is not the case. And thermodynamics is covered in every field. So everybody has to take it at one point or another. Anyways, that is what's very different. And I don't know if that comes across here in this little description, but that's what I wanted to make sure I took a moment to describe and to say here. Also in this part, and again, here's where our number has changed, and it's too bad I didn't upload the new one. But it is put here correctly, I think, on your syllabus there. that remember that Friday afternoon problem solving workshop. Highly recommend it. We now have changed the name. It's called Physics 123W for workshop, and then the number 123 matches then the class, and so there was that and some other reasons we changed the number. So ignoring the 199, you guys will recognize it with Dawn. And so those of you who are familiar with Dawn and working with Dawn, I probably need to say no more. For the rest of you, I would encourage you to sign up. I got the ad codes right here, so please see me after class. Let me tell you more about it, but it's well worth the 1 unit. Friday afternoon, he does the review. For those of you who've worked with Don, is it worth it? Yeah, absolutely, huh? Right. So encourage that. It can make a difference. You can quickly change a B grade to an A grade, or a C grade to a B grade, or just pass because you went to it. Going into the textbook material, I've got the textbook there. It says with modern physics, and I don't care if you use the 7th or the 8th, or this semester there's a 9th edition out, but since none of you are probably buying the book, that doesn't matter. But it does say that, I think, on the new syllabus here, yeah, the 7th, 8th, or 9th edition. And so make sure you have the one with modern physics. So the lab manual, did I bring mine? I did in here somewhere. Here is the lab manual. Make sure you get over to the bookstore and pick up a lab manual. And we're going to get started right away. There's no, hey, let's get acquainted first week like we did in Physics 121. We are right in the middle of the book. We are in chapter 15. You know Newton's second law. In a few minutes, I'm going to get started and write Newton's second law on the board. I'm going to do a bunch of calculations for you, and I hope you're ready for it. But what that means then is tomorrow we're going to do a lab. We're going to do a lab exactly on the stuff we're going to talk about here in the next few minutes here. And so make sure you pick this up. Some of you, like I said, will be doing the lab in the morning with Don, others midday with me, or in the afternoon with me, or others of you on Thursday with me. I'll turn the page, or in this case, scroll down, see how much has changed between this year, not too much, other than to point out that the next page is a long list of what I call additional help page. So if you find yourself struggling, these are kind of a good place to come to. If you come talk to me, that's what I'll go through and say, okay, what would help you get a better grade? Hopefully the first obvious thing is that you are reading the book, you are coming to class, you are taking notes, you are trying the problems. But in addition to that, the MC class, or the physics now called 123W, it still says 99 there, but corrected here, is that's designed specifically for you guys. So I'll say it again, I've got the you who are new here and not familiar with it, highly recommend it. You just go there, you do the homework from this class. There's not an additional lecture, there's not additional problems to do. It's for this class. Oh, we also have some free tutoring available. I'll set up the schedule this week. That always starts the second week, and so that's what I'll be working on this week. I'll let you know more about it next week. But to be quite honest, your tutoring is really here with Dawn. That's the main thing. Not to say you can't use that. I do encourage you to do that. And our two tutors that are there have already gone through our program and I think are excellent, and they know the material. So, go at it. Feel free to use that. Also, as some of you already know from having me before, last semester we finally got all three, Physics 121, 122, and 123, all video recorded and all loaded up to YouTube. And so you'll see them all there. In fact, you'll even see David in the back. So David's going to videotape it. And we're going to add to the Physics 123 one there. But the 123 from last year is all out there, all however many lectures there are in a given semester, something like 28 or something like that here. And so they're all there posted from last year, and we'll add to that and post more from this year in the syllabus. There's some other options. I'll kind of skip over those, but going down in order. Actually, maybe I shouldn't. I should at least say here, because I think this might help you out. If not in this class, that next one there, the optional book, there's the Sham Outline series, which I think are just phenomenal. You need syllabus? Yeah. I think are phenomenal. Highly recommend them. And if you find yourself ever struggling, and I'll add to it any class, because if you're like lost in your math class or your chemistry class or your economics class, I think the Shams does a good job of, after you've read the textbook, to come through and they can just give you kind of a concise, short outline of it. And so I really like those. MIT, of course, is great. Even your author's websites are great. And these old 1970 videos are even pretty good too if you got time to go to the Learning Center, but I don't know if anybody does. Everybody just goes to YouTube these days here. But in the old days, you would go to the Learning Center and check out the videos. So the fun part of that is just to get it on Laserdisc. It's like, whoa, look at this. What the heck is a Laserdisc here? And then you can, like Newton's second law, they got these three guys in plaid bell-bottom pants and doing their little physics experiment. So that alone makes it interesting. All right, but going on to the homework assignment, this is just like all the other ones. You'll see we get started right here, chapter 15, and we're going to go through as far as we can get into modern physics. We'll see how much we can cover. We will definitely cover quite well 39, 40, and then even in 41, and we'll get parts of 42. Usually in the past, 41's been right there at the end. That's the part where we do it and we say, well, you're going to do it, you're responsible for it, but no homework assignment. So we'll see how it plays out towards the end. And I suspect it'll be exactly the same thing. But I wanted to focus this first part then on chapters 15, 16, 17, and 18. And that's our first 4 chapters. That is part 2 of the book. And after that, we will switch gears and go into thermodynamics here. But for the next couple of lectures, that's what we will be working on. In fact, let's look at the schedule here. Because again, the layout of this class is a little bit different than the layout of the other classes here. And we have 4 parts. The first part is our oscillation and our waves. And we are going to be tight for time, and so we're going to do this first part really, really quick. I mean, look here carefully. The good part about it is I think we can do it quick. There won't be any new physical principles. We'll be just applying Newton's laws of motion and all the mechanical principles we learned in Physics 121. And so this is a good start to the semester in the sense that no new physical principles, applying what we've already learned, but it's been 6 weeks or more since you've done Newton's laws. So it does make a nice review as we get started. But it does go pretty quickly, so keep your eye on this. In fact, I'll point out, look at what we're headed for here. I think I have a laser pointer somewhere. But we're headed right here. This first week, we're going to do chapter 15. Looks like a low battery here. All right, but chapter 15 right there. And we have all week to do that one. And the purpose for that is so that we can spend this first time getting acquainted, getting the syllabus, and get started. It is probably the longer of the 3, but then we have just a short time frame. And 17 is actually a pretty long chapter, and we're only going to give 1 day to it. So next week, we're going to do 16 on Tuesday, 17 on Thursday, and then 18 on next Tuesday. And so we'll do what we can. The truth is we probably won't be able to cover every section. But if we don't, that's okay, I guess. But I do want to keep on pace so that we can get, into this 42 at the end. And so kind of our chapters that we can play around with a few sections are in here. All that is to say, be aware. We're going to go quick, and we're just going to jump right in. And read it ahead of time then. I'm sure many of you remember me saying that last semester, so much so that I'm sure all of you have already read chapter 15 before you came to class today, right? Knowing the lecture was on chapter 15, and so now you're going to listen to the lecture, and then you're going to read it the second time. So you've already read it like a novel, and now you're going to read it like a textbook after today. But if you haven't, when you leave today, read the 15, but also read into the 16. And then the next time read into 17, and the next time into 18 as we get started. Oh, I'm sorry, I misspoke. We're not doing 16 quite yet, are we? 16 isn't until Tuesday. So you got the weekend to read 16. All right. But look what comes pretty quick. And look how it's labeled. It's a half. That's exam number 1, if you will. And that's what I wanted to point out. It is a little bit different. Since this material, we're going to go kind of fast. We're not going to go very deep. I'm going to call this half a test because the same thing's going to happen down here. Half a test. And so I don't know if it's better to call it 2 quizzes or 2 half tests, but it's the way I guess I've just set it up over the years. It matches my other classes is you have 3 exams.
So there's 2.5 questions.
So what's going to happen is we are going to have 2.5 questions, although that rounds to 3 because we'll have 1 easy question in there covering these 4 chapters. And so on this day, Tuesday looks like the 18th, we will have a 3-question test. It'll be 1 hour long, and that will be counted as half a test, so 50%. It will be combined with this test, which will be our modern physics, which again will be a test that will be 1 hour long, and it will be 3 questions or 2.5 questions, and we'll combine them together to make 1 test. So as far as the scoring goes, those 2 make 1 test. That's what I'm trying to point out. So test 2 is right here on thermodynamics, and test 3 is on optics. And there's some pretty significant and meaty stuff in there. And you will want and need the whole 2 hours, and you will want the 5 questions that we normally have. So again, a little bit different, but other than the test is divided into 2 pieces, the setup of this class is like Physics 121 and 123, where we have 3 tests and then a final exam here. Yeah, and then we're going to do a lecture after the half test or quiz, whichever word you want to put there. And that, again, we need the time for that. So we're covering a lot of material this semester. Some of it maybe not as in depth as others. In fact, none of it ever goes that much in depth. But by the time we get to the end of thermodynamics and optics, we're getting see how the first chapter starts easy, and you're going to go, oh yeah, this is easy. And then we get to that 4th chapter, you're going to go, whoa, that came out of nowhere. Now, all right, let's see. What else did I pass around? And I did do this, right? Did you guys get the homework assignment? All right, so just like before, I have photocopied chapters, it looks like 15 through 18 for your homework. So that you have, that's what you will be turning in. So due next Tuesday will be this chapter 15, and as much as you can look ahead into 16 and 17 and 18, I think it will be well served. You need one of these? Actually, take a couple back there. Pass those around there. People who came in late. And syllabus, yeah, take a couple of those. And I think you guys got the standard bookmark, right? That where we will post the solutions. And so after the due date, I'll post the solution so you can kind of double check them. Or, of course, those of you who know Don and work with Don, Don has the solution manual. So as long as you've convinced Don that you've given the problem a try and you're not just checking it out to copy the solutions, he'll let you see it before you turn it in and double check it, and then that way you will hopefully redo it. Well, how did I work there? Oh, good. I want to take about that first half hour or less, and so it looks like we're a little bit less to get the class started. Any questions? Make sense? Shall we begin? And pick up here where we have left off. All right, so I'll get rid of the overhead here and turn off that. Grab me a pen and grab my lecture notebook. Let's see, this is the lab manual, so here's the lecture one, and start off by doing a quick review, and one that I hope you remember because we are going to extend out. And so I'll say here, let's look at part 2 of the book, chapter 15. As I already pointed out, your author has titled this Oscillations and Mechanical Waves. And so that's what we will be studying for these next 4 chapters. And that's what your first test or quiz or half test, whatever word you want to put in there, will be about. That 1 hour, 3 questions will be on oscillations. In fact, probably not a surprise to you. If you will have looked up here, you will notice there are things that tend to oscillate. And so let's look at all these. But before we do too much here, let's go all the way back to Newton's laws of motion. And in particular, let's look at Newton's second law. Maybe I should ask you guys, coming back, you guys remember what Newton's second law said? All right, it says the sum of all the forces, which we called net force, is what? Is equal to mass times acceleration. Or, if you liked it described this way, which I kind of do, but mathematically I prefer products over quotients, but physically I like it described this way. The acceleration is determined by 2 factors. One is the net force, and the other is the mass. So the forces tend to make things move. The mass tends to resist that. So that's what we learned in Physics 121. Haven't forgotten that, I trust. In fact, a quick review problem from Physics 121 might look something like this. I might take a box of mass m. I might pull on it with Fem force F at some angle theta. As it is sliding across the surface, then it may have some friction, so we'll call that a kinetic friction. The table or whatever this block is resting on would be pushing up. That would be a normal force. And of course, there would also be the effect of gravity. And so what we like to say is draw the free body diagram, right? That was our step 1 and step 2 of solving this problem. Step 1, got a good physical picture of what's going on. Step 2, write out and draw the free body diagram. And once you get the free body diagram, you can get to step 3, which says, let's write out the equation. And so we were first introduced to this in chapter 5. We continued for the rest of the semester with it, and including going into this semester. We are going to still use Newton's second law here. And again, if I were to apply this logic to this problem, I would start off and say, okay, the force from my hand in the x direction would be F cosine theta. Gravity in the normal force has nothing in the x direction, and I'm going to be just using the traditional coordinate system. And then the frictional force would be in the negative x direction. And so that would be the sum of all the forces in the x direction. Fair enough? And then that would have to equal mass times acceleration in the x direction. If I did the same thing in the y direction, I would say, okay, the force from my hand would be F cosine theta, so this one is pushing up. The normal force is also pushing up, so there's another positive. Gravity is pushing down. There is no vertical component to the force of friction. It's all in the horizontal direction. And so that would have to equal mass times the acceleration in the x direction. So again, all this was based on Newton's second law. But maybe this will help you. You guys want the answer to all the homework problems this week? Here it is. Here. Guaranteed. We're going to start right here. Right here, draw the free body diagram, write out the equation, solve the equation. End of story. It's that simple. In fact, especially for those of you who are new or haven't had me for a while, what does it say across the top of my syllabus and every test? Physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. And that's what we're going to see. And so the good news here is there's no new physical principle. It's Newton's second law. Now, we're going to apply it to situations that we did not apply it to last semester in Physics 121. As you can see, we're going to do things that are going to be oscillating, and we didn't do that before. But the truth is, you could probably figure it out all on your own, because all you got to do is start here and write out the forces. Okay? And that's why I'm reviewing here in these first few minutes. And so these would be our two equations. And I'll say it again. Step 1, got a good physical picture of what's going on. Step 2, draw the free body diagram. Step 3, write out the equation. And of course, step 4 is then solve that equation. And by solving that, of course, that involves math, but it also might involve a little bit of physics. For example, in this particular problem, if this box would be sliding across the horizontal surface of this table, what could we say right here? Yeah, and so our first step into solving this for step 4 is to look at the physical picture and to realize the acceleration in the y direction is 0. And that becomes useful in the sense that then, as we simplify the math, we see that the normal force is equal to that. So that when we come up to here, and of course remembering that the kinetic friction is the coefficient of kinetic friction times the normal force, then this equation involving the y's can be substituted into this equation involving the x's. And so that's what happens as we get to the final step, step 4. But let me say it again, because again, I want to just emphasize we're going to be doing the same thing. It just won't be cases that you've seen already. We are going to start off by saying, got a good physical picture of what's going on? Draw the free body diagram, write out the equation, and solve the equation. Now, if we were asked to solve for this equation, and why don't I just go ahead and do that? Let's see. I think we've got some similar, well, maybe I better take a couple of steps here. I'll write that one out. This will be a minus a mu k mg. This will be a plus f sine theta. Is that a plus? Oh, yeah. That's what I'm missing. Mu k. And then that equals to mass times acceleration in the x direction. So if we were trying to solve for the acceleration in the x direction, which typically is the type of problem we would have, we might put these two terms together and say it's the force from your hand, cosine theta, plus mu k sine theta minus mu k mg. Right? And so we would now have finished the problem with Newton's second law. Okay, and so there is, like I said, kind of a review problem. And it's not so much a review in the terms of force of friction, but it's more in a review of how did we learn the fundamental principle so that we can solve any problem. Oh, did I make a mistake? I did. How's that? Okay. Thank you. All right. And again, I didn't think I was going to carry it out quite this far to the end of the math, but carrying it out to the end, we get an answer. So here is where this semester begins. Let's do the following. I've got a bunch of springs up here. I don't have a simple one of no friction and only one spring. I wish I had something as simple as that. But why don't we look at this one for a moment. For those of you who can see, you can see that it actually has two springs. But let me, as I said, kind of oversimplify this for just a second and say, let's take a look at what might happen in the simplest case. The simplest case being, what if there was no friction and only one spring? And that's where we want to get started. So we got to review springs for a moment. Anybody remember chapter 7, Hooke's Law? He's the one who discussed springs and the force from the springs. What did we learn in chapter 7? I had a spring, and it has a natural length. And then I pull the string a distance x. Do I get a force? Yeah. What direction and how do I calculate it? Right. So the force is opposite of the direction x. In other words, if you pull the spring in the positive direction, the spring pushes in the negative. If we were to compress the spring, push it in, which way does it push? In the opposite direction. So the negative sign allows us to always get the math appropriate that says what direction is the force from the spring. It is opposite to the direction that you have either stretched or compressed the spring. What was the K? Do you remember? Okay, good. That's what we called the spring constant. And it was a measurement then of how tight or loose the spring was. This spring is the one you guys are going to be using today in class, or I shouldn't say today, tomorrow in lecture and lab. And so you guys will measure the spring constant of this one. In fact, step 1 of the lab tomorrow is to hang it down here and keep pulling on it and measure how much force there is and measure how long it is, and you will get some data. You will put it in here and you'll say, okay, I'm going to pull on this spring, I'm going to give a certain distance. And at first you will pull it just a short distance and get a small amount of force. Then you will pull it a little bit more and get a little bit bigger force. And again, and if I remember right, you're asked to do it 5 times. And hopefully what you will have is a nice straight line, because the slope of that line would be linear, and it would be this spring constant. Yeah, exactly. It would be the constant. And so as we look at that equation, we see that our data gives us that spring constant. And so again, maybe not too new other than the fact that we've talked a little bit about springs in chapter 7, but it was only a little bit, and now we're going to go a little bit further here. And so that's why, again, step 1 is to just kind of remind you of what is the spring constant. What would be the units of the spring constant? I mean, let's say it comes out to be 9. And in fact, maybe I'll just give you some heads up, because that's what you should find tomorrow. These springs are around 9. At least the majority. We have some other ones in there. So, but most of you will get these brass ones that taper to the big side as they go down, and you will find the value somewhere around 9. 9 what? Yeah, Newton per meter. So again, looking at this formula, this spring constant is saying something about how strong the spring is. 9 newtons per meter means what? Yeah, it means that if I were to take this spring and not pull on it at all, its natural length right there, and then if I were to pull it 1 meter, I don't know, is that about a meter there? Then how much force is it pulling back? 9. So it pulls 9 newtons for every meter that I pull it. And if I pulled it 2 meters, it would pull back with 18, right. And so this constant is telling us something about the strength of that spring. And some have big numbers and some have small numbers. And the one I have out here is relatively small. It's a good one to work with for the lab. It's just about the right value for us. And that's why we will have it. So 9 newtons per meter. All right, so if you remember all that, then finally we can work on a problem. The first and simplest problem of this new chapter is what would happen to an object that was simply this. You take a surface, a frictionless surface, and you place an object. Now I don't have a frictionless surface, but I do have a cart that's on wheels, so it's pretty good. Not completely frictionless, but not bad. And then, if you were to take a spring and hook it horizontally here. And so I know I have this one vertically, but let's wait a few minutes to talk about, well, what about the additional effect of gravity? So I'm trying to avoid the effect of gravity here. Keep it as simple as we can to get started. And I just hook a spring to it. And that's its natural length of the spring. So again, imagine just one spring here. So I've got one spring. I've got an object. This is the natural length of the spring. And what would happen then if I pulled it a small distance and then let it go? What kind of motion would this object have? Well, you can probably see already why I put it out here. It begins to oscillate. You can probably see then why the title of part 2 is called Let's Examine Oscillations and Mechanical Waves. But let's prove that here. Let's take this spring constant K, mass M, frictionless surface, and let's go back to Newton's second law. Let's add up all the forces in the x direction. Let's add up all the forces in the y direction. And let's see if we can apply the lessons we learned last semester of, all right, step 1. You got a good physical picture of what's going on? The simplest one I can make here at the beginning. A single object with a single spring horizontally. It's the easiest we can make it. No friction. All right? So we're going to start there. Good physical picture. Step 2. Free body diagram. All right, so help me out here. What are the forces on this block? Okay, gravity's pulling it down. mg. Okay, I heard a normal force from the table, and I heard a force from the spring. Let me call it minus kx. I'm a little reluctant to say what direction the force is, because if this is where it starts, obviously when I pull it to your right, my left, the force is the other way. But once it moves back to its starting point and beyond, now it's compressing the spring, so which way's the force? Yeah, the other way. So maybe the best way to describe the force from the spring is to put maybe an arrow in both directions, saying, well, at some moments in time the force is one way, and some moments in time the force is the other way. Kind of depends where it is. Obviously at the beginning step, it is truly just over here. It goes that way. But that would be all the forces, right? And in fact, the reason I picked this one is because really the motion could be studied with only the x. We don't even have to look here at the y. I mean, I'll write it out for completeness. The y would say normal force up, gravity down, equals mass times acceleration in the y direction, but the acceleration in the y direction is equal to 0, just like, well, I guess they've erased it, but just like the one I was trying to do as a quick review here. And so nothing real exciting about the vertical direction. It's the horizontal direction is where I want to get us started here. And so in the horizontal direction, I would say, okay, add up all the forces. Well, what are the forces? Now there's only one. It's minus kx. And again, what's nice about the math with the minus sign there is that means if x is a positive number, what direction is the force? Negative. But if x is a negative number, which way is the force? It's positive. And so this little equation with the minus sign takes care of the direction, a plus or a minus. Perfect. All right. So that's the forces in the x direction. And that's all there is. And that has to equal mass times acceleration in the x direction. And that's the equation here to get us started. And so that's step 3. Let me review again. Good physical picture of what's going on. Free body diagram. Write out the equation. Now, last step, solve the equation. And I claim that once we solve this equation, we have the equation of motion. Where is this object? What kind of motion does it have? And the reason we kind of waited until chapter 15 to solve this one is this isn't such an easy equation to solve. Although you guys who went through Physics 122 hopefully recognize it. It looks a lot like an LC circuit. For the rest of you, let's go through this. And maybe even for those of you who went through 122, let's write it this way. I'll leave the minus kx alone. But on the other side of the equation, where I have an acceleration, let me remind you that acceleration is what? The derivative of the velocity, and the derivative of the velocity, or the velocity comes from the derivative of the position. And so what we have is an equation that can be solved for x, right? We've got an x on the left-hand side. We have an x on the right-hand side. It just happens to have a derivative in it. All right? And so this is why we waited until second semester before we addressed this one. Because what's the answer to that one? Yeah, and maybe it would help, I know it does for me, to write it this way. And I know a few moments ago I joked with you about, hey, you want all the answers to all the homework problems? And although it was a joke, I was dead serious that it literally is this, write out the equations. But let me take this one step further. Because every problem you'll do in this homework, and I've seen students in past years really struggle with this first homework assignment, they miss this very simple point, okay? You're going to write out the forces, guarantee it. But every one you write out comes out to look like this equation. That's what this chapter is all about. All the scenarios that come out that look like this. So don't be surprised if it looks like this. And now let me show you how to solve this equation. Because everyone you come across in the homework has something that says second derivative of the function equals a negative, some constant, and the function back. And so you need to know what that solution is. And so some of you, obviously half of you went through this with 120 in the electronics with me. What is the answer to that? What function can you take its derivative twice and get a negative out in front and the function back? Cosine will work. Any others? Sine will work. Any others? E to the negative x? No. Tempting.
Negative e to the negative x?
Negative e to the negative x? Tempting, but no. Yeah, it was a month and a half ago, wasn't it? And there are only the sine and the cosine. But let's take a look at all of those here. Let's do a quick little math review. I'll start with the cosine function. If I were to say, let's look at the cosine of, and I'll put a t in here. In fact, maybe I'll just put some constant, so I don't want to use a constant that we're going to see later. Actually, well, I'm going to start keeping it simple. Cosine of t. Okay, so a function of time. And so I'm going to take the derivative of that. Now notice I'm writing the function as a function of time, not as a function of x. This is not y is a function of x. This is x is a function of time. So maybe I should write it that way here. So if I were to take this function, if I were to take the function x as a function of time equals cosine, if you take the first derivative of that, what do you get? Yeah, negative sine. If I take the derivative yet again, what do I get? Yeah, negative cosine. So those of you who said cosine would work, you're right. And that's what I wanted you to see. And so it may be an equation that you haven't come across from, but it's not beyond your ability to see what the solution is. It is what in math we would call a second order differential equation. It's the easiest second order differential equation. So those of you who've already done your math of differential equations, I'm sure this looks trivial to you compared to the ones you've seen. But this one is simple enough that even though you guys, some of you, many of you, haven't had a formal differential equations class yet, I think you can see it's pretty easy to observe what the solution is. Cosine function does work. Some of you said the sine function. Agreed. That would work too. Let's give it a try. Sine function, does that work? Sure. Take its first derivative. What are you going to get? Cosine t. Take its derivative again. What do you get? Yeah, minus sine t. So you can see that you get a minus and then the function back, right? Okay. Now, there's going to be a lot more to this, but let's start with one that doesn't work. Somebody said, what about e to the minus x? Okay, so take the derivative of that. What do you get? Minus e to the minus x. Take the derivative of that. What do you get? Yeah, you get a plus. You get another minus when you take that derivative. And because of that, you don't get the minus and the function back. Had this been a plus sign in front, then I would have been saying the solution is an e to the minus x, but not the sines and cosines. But that's not what we have. We have the minus sign. So that's an important piece in our puzzle. Somebody else said x is a function of time equals minus e to the minus x. Again, good try. Won't work. Because if you take the first derivative, what do you get? Yeah. You get e to the minus x. You take the derivative of that. What do you get? Minus e to the minus x, which is the function, right? So you got plus the function. You did not get the minus of the function. The minus was part of the original function, so you've got to think of it as part of that original function. So you've got to be able to take the derivative twice and not only end up with everything that was part of the original function, but an additional minus sign in front. This is not an additional minus sign. This is part of the original function. So no, that doesn't work. And there's no point in looking for more of them. One thing that you guys will learn here is the number of solutions, just like the number of solutions in a polynomial. If I had a quadratic equation up here, how many solutions would there be? 2. If I had a cubic equation, how many solutions would there be? 3. And so likewise, I have a second order differential equation. How many solutions are there? 2. And so we found them. We found the 2. The 2 are either a cosine function or a sine function. And in fact, I'll do you one better. What's the difference between a sine and a cosine function? Yeah, aren't they just phase shifted a little bit different? And so I would say that a sine function is really no different than the cosine function. And so why don't we say the solution to this equation is really a cosine t plus some kind of phase shift. And so maybe it's worth doing some little math review here. What is this phase shift? And so we'll just refer to it as its phase or its phase shift and say, okay, how far is it moved left or right? If I were to put a grid on here, here's time, here is x, and I were to start off with something that begins at its peak and tapers down and then comes back, That looks an awful lot like a cosine function. What would be the phase shift for this? No. Yeah, oh good, 0, right. 0. This is just purely a cosine function. This function truly is just cosine of t. Right? What would, maybe I'll change colors here. What would this one, which looks like a sine function, what would phi be there? Yeah, minus pi over 2, right? This is like thinking about the origin starting with just a pure cosine function, and then what you've done mathematically is you have actually grabbed the origin and pulled it back a pi over 2. And so what that means then in this function, that when time equals to 0, you really get a minus pi over 2 for the cosine function. And so we have shifted the origin. So here's the neat thing about that. Notice that I don't even think of this as two solutions, do I? It's really just a cosine function with a phase, right? In fact, I'll change colors yet another time here and say, what if the function looked like this? What does that function look like? Yeah, and that one is like taking this original cosine function. In fact, maybe I should take original cosine and extend it back. But it looks like I have taken the origin and pulled it back a whole pi. So I would say the phase is negative pi, which, by the way, is really the same as pushing a forward pi. So in this case, I'll put a negative pi or a positive pi, since I'd get the same thing going either direction. Well, I'll put the last one up here, or at least I should say the last simple one, because they could be something in between, you know, a perfect pi or pi over 2. But what if I had a function that looked like this? It started here, went down, came up, went down, came up, went down, came up, went down, came up. What would phi be there? Yeah, again, going to the black one, looking at the original cosine function, this would be the same as taking the origin here and pushing it forward pi over 2. So this would be a plus pi over 2. Notice that a minus pi over 2 does not give you the same as a plus pi over 2. And so this one is the equivalent of a negative sine function. The other ones I don't think I put, I guess I should. This one here is the equivalent of a negative cosine function. This one here in the green is the equivalent of a sine function. And so my point being here is that instead of me saying the solution is either a sine or a cosine, I'm going to just say it's a cosine with some kind of phase. Okay? And that's what I'm trying to show you at the beginning, which is obviously what you need to see, because I'll say it again. The key to this chapter is right here. Every problem we will do, whether it be on the homework or the exam, will be exactly this. Draw the free body diagram, write out the equation for the forces, you will get an equation that has a function in it where on one side you'll have the second derivative of the function, and on the other side you will have a negative and the function back. It is these kind of solutions that come out to oscillate. That's the whole point of this chapter, looking at things that oscillate. And that's why every single homework problem you do, and some are easy, like this first one, and some are really hard, like the last one, but they all do the same equation at the end of the story, that they will have the second derivative of the function is equal to a negative, some constant in front, and the function. And what I'm trying to show you then is the solution to that is a trigonometric function, a sinusoidal function, or cosinusoidal function, whatever fancy word you want to put there. Okay? The phase could be different depending on how it got started, and so that's why we're going to write it in the equation as just phi. I mean, let me explain here. If I were to come over to here again, and I were to grab this little mass, and I would first pull it to your right, and calling the positive direction your right, and let it go, doesn't it oscillate? Doesn't the equation say the solution is that it's oscillating? And did you catch this part? What is phi in this case? And this tends to be the challenge for students in this first chapter. I'll say it again. Watch. I pull it to the right. It starts to the right. It starts at its maximum, and I let it go. What function is that? That's the black one in here, right? The black one in here is the one that starts at its highest position, and you let it go. That is phi equals 0. That's the part of the physics you need to catch, because it won't be in the math. You've got to decide then, if the solution then is a cosinusoidal function, what is phi in that case? Because it could have been different. Could have been this. What if I were to take this little part and move it to your left, calling that the negative direction, and letting it go? Does it oscillate? Well, yes, it follows this equation. But physically, which one is it up here? What phi is it? Yeah, the red one here, right? The phi is a negative pi or a plus pi. This is a negative cosine function. This is the one that would start down here at the negative position and then go back to equilibrium and then go positive, negative, positive, negative. The green one is a sine function. That means it starts at 0 and goes positive first. So at time equals to 0, it's at 0. But it's moving that way. Time 0. And so if the problem said we have a cart on a spring and somebody comes along and hits it to the right, what is phi? Pi over 2. And I think one of the most challenging parts of this homework one is getting students to see that physical picture. You've got to pay attention to what is the meaning of the math. I'll say it again. You want to be able to read the math. It's not just do the math, it's read the math. The equations we're about to give, you can't just blindly plug and chug. I mean, you'll get like half of them right. You'll do okay. You'll get an okay grade. You'll transfer to an okay school. You'll marry an okay spouse and have okay kids with an okay salary. You know, we've been through this before here. But that piece of it is all pure physics. And it's so easy, students get stuck on that one. And that's why I'm trying to warn you about that. How would I get, oh, question.
Yeah, sorry, did you say when you hit it to the right, it's pi or not pi?
Let's see. I'm hitting it to the right, so it's going positive first. So it's the green one, which is minus pi over 2, yeah. How would I get the orange one? Yeah, and so the orange one would physically be represented by right? Now for the hardest ones of all, does it have to be exactly pi or 0 or pi over 2? Could it be like pi over 4? Let's talk about pi over 4. Let's start with first, what would it look like? Do I have any more colors here? Oh, I got a blue. All right, one more color. What would phi equaling pi over 4 even look like on this graph? Positive pi over 4. Right. Yeah, and probably the best way I like to do it is, again, think about the original function itself. Okay, cosine function. That's the black one. And the phase is how much you're shifting the origin. It's like grabbing your hand and moving it back and forth. So I'm saying move it a plus pi over 4. All right. So if you imagine starting here and moving it to here, this would be the starting point. All right. So it would start here and be heading down. And so it should reach bottom maybe about there. And that means it should peak right about there.
Shouldn't it go farther down and higher up? And lower, not all the way, shouldn't it go past the black line on the bottom?
Well, okay. You're asking about the amplitude, and I've been trying to give these all the same amplitude because that's my next discussion.
Wait, no, I know. That's why shouldn't it be?
No. So let me let me try to give it the same amplitude, just a different phase. Okay. Because hold on, let me get into the amplitude effect. Boy, there's getting so many on here. Between here like that. Something like that. All right. So the two things I want you to see in this phi is mathematically, how do we handle it? And physically, how do we handle it? Because you're going to have to put those together. Sometimes they give you the math and you have to see the physics. Other times they give you the physics and you have to put it into the math. So in this case, I'm giving you the math. I'm saying, okay, let's write a positive pi over 4. And so what that means is that time equals to 0, it is in the positive position, but it looks like it is heading back to equilibrium in the other way. So how would I do that on here? Yeah, so its full amplitude may be out to here. And I wouldn't have it that far. I'd only have it at part of its amplitude. Looks like 0.707 of its amplitude. And but I would be also at the same time give it a little whack. But maybe not quite that hard to keep it on the track. But okay, so maybe I'll make full amplitude here, partial amplitude with a little whack. Okay? And so we have both effects. We have the effect of starting not at 0 and also a little bit of a tap to get it to going. And so like I said, I think one of the hardest parts of this first chapter is really the math related to trig functions. And so that's why I decided that, okay, this first day here, what I'll do is kind of just write out the equation and stop and talk about the solution for a little bit. I'm hoping you saw that the solution works for either sines or cosines. I'm hoping you're also seeing that that means just a difference in phase, and because it's this one that, of the three variables we're about to talk about, I think it is the phase that have given students the hardest troubles, and that's why I wanted to draw all these. But let's go to your question. Your question is about amplitude. I've drawn a bunch of them up here. Do they all have to have the same amplitude? No. What would determine the amplitude? Yeah, let's go back to the easiest one, the one in black. I'll move on to a new graph so I don't have to keep looking at this one. But it is quite possible, certainly physically, And maybe I should leave this up here, because that's the equation we're going to be studying. That's the solution to all the homework problems right there. Okay? But if I were to have a phase of 0, which, as we already mentioned, a phase of 0 is pretty easy to get physically. It's just move it to the right and let it go. And it will start at its maximum position. But I could have something that looks like this, but I could also have something that looks like this. Let's talk about it physically first. How would I get these two scenarios here? Yeah, the first one, which we might call a small amplitude, is I would pull it just a little bit and let it go. And so maybe I've pulled it 2 centimeters to the right, positive, and let it go. But if I were to pull it more, like 4 centimeters, and let it go, well, then it would look like that second graph I have up there in black. And so these have different amplitudes. How does that come into play in our math here? Yeah, good, you guys are noticing. These are not complete solutions yet. In other words, you first told me sine and cosine work, but I kind of merged those together into this. But what if I had a number out in front? Let's call it A for amplitude. This one I think you're most familiar with. Most students don't have troubles. They remember this from their trig class. That number out in front does what? It's the scalar factor, right? It's on how big this gets. You guys, I think, remember from your trig class that the regular trig function has a maximum of 1 and a minimum of -1. So if you wanted something to go back and forth between a positive 2 and a negative 2, then what number do you put out in front? A 2. If you wanted it to go back and forth between 4 and -4, what number do you put out in front? 4. So that number out in front is probably the easiest one. It's certainly much simpler to talk about than that number. And maybe I should have done it first, so I didn't have to scare you with this one at the first, but thought maybe I'd get you while you're still fresh before I started tiring out there into the lecture there. But that's what that number out in front. In fact, let's just double check that, because we didn't have an A when we checked to see if it was a solution. By putting an A in front, does that still work? Is it still a solution? Yeah, it really is. I mean, let's give it a try here. Watch. If we take x of t and we put A cosine of t plus phi, if we take the derivative the first time, well, what do we get? Well, the cosine becomes a sine, right? And we still got the A. Oh, it becomes a negative sign. Thank you. Yeah, and there's my negative. And then when I take the derivative a second time, the sine becomes a cosine. The A is still floating around there. There's no more negative sign, so we have the original negative. Not original, but the negative from the first derivative. And so that would be negative of this whole thing. But this whole thing is the original function, right? So we do have the second derivative of the function equaling, and there's the negative, and the function back. So the A is just part of the function. So the A in front is perfect. And hopefully it doesn't surprise you that we have some constant, and in this case 2 constants. Did you catch that? How many solutions do we have? 2. How many constants do we have in that double solution? 2. Now, of course, the reason for that is when you go to solve an equation like this, aren't you really integrating twice? And every time you integrate, you get a constant. So, not a surprise that the solution to this crazy equation, for those of you who haven't done it before, has 2 solutions, which we're going to write with a phase, and then those 2 variables there are the constants of integration. Now, we don't need to worry too much about the math. That's not the author's intent here. The author realizes that this book is written at a Math 160 level, and he's throwing out a second-order differential equation, which is a little bit beyond your Math 160. And so that's why I'm taking this extra time to say, okay, many of you have not looked too closely at this equation, but this does have a quite reasonable solution, and I want you to understand it, because I'll say it again. Every single problem in this chapter is about that. Every single problem is about writing out Newton's second law, and sometimes that will be translational motion, and sometimes it'll be rotational motion. Torque, moment of inertia. We'll get to those. But the translational motion is what we start here first, the easy ones. But when I wrote it out, you'll see that what I got was an equation that said, take a function, take its second derivative, and what you will get is a negative and the function back. You also get a constant. I haven't talked about the constant yet, so we've still got to build on this. But we have seen that this would be a solution. It's not the complete solution, because I haven't talked about the constant out in front, but we're almost there. And so now I think you understand what the A physically represents and mathematically represents. So if they give you it mathematically, you can see how it relates physically, or they give you a description physically, you can put it in mathematically. Phi perhaps was a little bit harder, but I think you're beginning to see that if they give it to you mathematically, you can see how it works physically, or if they describe it physically, which they usually do, because they usually say something like this: take the cart, pull it to your left, hold it there, let it go. Huh. Well, that's the red one, right? Hold it there, let it go. That is a cosine function with a minus pi. Or if you just want to make it simpler, just write it as a negative cosine function from the very beginning. Okay?
T would be 0. Just write it like that.
You could write it as cosine t minus pi, or you could write it as minus cosine t, minus cosine. And since that one seems simple enough, I probably would encourage you to do this one. Or you could even do a trig identity on this, right? What is the cosine of a plus b? Isn't it cosine of the first times, oh, I need to think here, cosine of the second minus sine, and I'm thinking of this, by the way, as plus a negative pi, because a plus b. So a and b minus sine a sine b. And of course, sine of negative pi is 0, so that is going to go away. Cosine of a negative pi is negative 1. And so this all equals negative cosine t. Not a surprise. So again, whatever math you want to do or whatever physics you want to do, they should complement each other and they should agree. And so again, it will if you're doing a little bit more than just doing the math, but you're reading the math. You can do this by reading the math. You can do this by doing the math, is what I like to say. But either way, they're kind of the same function. So yeah, if I was doing the homework and they said, hey, pull it to the left and let it go, I probably would not start here. I'd probably just jump right to here and say, yeah, go ahead and begin. All right, let's see, where was I here? So you got the equation almost. We're not quite done, because remember, the solution to this said, take the second derivative of it and get, well, the negative of the function. That's what we talked about a lot. But what about this in front? Where does this come from? Because we haven't really got that yet. That's the missing piece. How would I be able to get the constant out in front? How would it fit into this without changing too much so that it still works as a solution? Any idea? Chain rule. Any idea? Chain rule. Oh, very good. Remember a chain rule, if there was a number in front of this t, what would you be doing each time you took the derivative? You'd be pulling it out in front, right? And you would end up doing it twice, wouldn't you? Ah, perfect. This constant out in front must have been the result of what was ever in front of the t. Here's what I mean by that. What if I, and I guess I'll have to erase this part of it, and finally get to what I want you to see today, and that is the solution to this second order differential equation. And everything else that we talk about for the rest of this chapter, which is the rest of this week, will really be the same solution. Different scenario. We might have things rolling instead of translating. We might have friction added. We might have 2 springs instead of 1 spring. But everything is going to boil down to understanding the solution to this type of equation. Because this type of equation always leads to the oscillations. That's what this chapter is about. If I were to say x as a function of t equals a cosine, I'll put the phase in there, I'll put the t in there, but let me do one more piece. What if I put the square root of k over m? Now I'll go through the math, but just kind of looking ahead, do you see what's going to happen with that square root of the k over m? Do you see that when you take the derivative the first time, it's going to pull out a square root with the chain rule? And then when you take the derivative the second time, it'll pull it out a second time. And of course, 2 square roots go away. When you have a square root squared, you don't have a square root anymore. And so watch what happens as I go ahead and I do this. And so I will take the first derivative. And then I'll leave the a alone. First derivative of a cosine is a minus sine. And I will have the square root of k over mt plus phi. And so there's my first, and then the chain rule. That was the whole point. Square root of k over m. And then the second derivative would say, okay, there's the negative again. I'll take the square root of k over m and the a out in front. When I take the derivative the second time, the sine becomes a cosine, and then the chain rule brings out a second square root of k over m. And so I will get a negative k over m a cosine square root of k over m t plus phi. This whole thing right here is the original function. And so I have minus k over m times the original function. Yay, I found it. Whew, took us a while. So let's not have to go through that again. All right? And that's my warning for you. Don't go through this again on the homework. You can if you want, but do this. Write out the equation of motion. You will find an equation that looks something similar to this, okay? And so all the problems we do boil down to an equation that look like this. And therefore, they boil down to a solution that looks something like this. And so compare what I've just done for you now with whatever problem you have. Thinking of the one that tends to give students a challenge is the one where it's a spring on a cylinder that rolls with friction. And so we've got torques and we've got spring and we've got moments of inertia, but write out the equation and I guarantee you'll get something that looks like this, okay? And so you'll see me do that. Between today and Thursday, I'll do this 5 times and we will come up with 5 of them, and on the homework you'll be asked to do it many other times. And every time we come up with that, we are going to say this is the solution. Okay? And we've, like I said, we've started here with the simplest case to show you that it wasn't hard to get to here. Sometimes it's going to be hard to get to this equation. But what hopefully won't be hard anymore is the solution to this equation. I just went through it. It is a sinusoidal function. Okay? And that is going to be it. Now, maybe I should have one more quick discussion here, because you've already told me, or we've already discussed, this one. Like I said, I think understanding that one's probably the hardest one. This was the amplitude. You guys seem to catch on with that, no problem. But what about this? What's this doing? Yeah. And so looking at the math, isn't that the part in front that changes the pattern here? Watch. You might be more familiar with the word frequency. That is the frequency. That is the rate at which it goes back and forth. How much time does it take to go back and forth? Let's do this. Let me give you a definition. Let's throw this word period out there. If you take a look at this card here, and again, to keep it simple, I'll pull it to the right and let it go. So phi is 0. I'll pull it 5 centimeters to the right. So A is 5 centimeters. And then I let it go. Okay? So it's going back and forth, right? It's my trig function. My question is, how much time would it take for one cycle? How much time would it take to get right back? That's what we're going to call the period. The period is the time for the object to move through one cycle. Let's call it capital T. And so our first new variable besides mass and phi and A, which I don't think those were new to you, this one might be. So when you see the capital T stands for period. Unfortunately, we also use the capital T for tension. And so don't confuse it. Not too many problems in this chapter have tension or strings, so we can usually get away from that. And torque, we use the Greek letter tau, so if we make sure we write it with a good squiggly on top, we hopefully won't confuse that. But here's what you're telling me mathematically. If this is the equation, then some time period later, shouldn't it be back where it started? Whether that be 0 back to 0, or whether that be 5 back to 5, or 7 back to 7, wherever. You take any point along here and you ask yourself, how much time does it take to get back to that same spot? Then it is the period. The easiest one is to say, okay, here's where it starts. How much time does it take to get back there? So if you let it go, right there, that's the period. The time for one cycle. Starting on the right, back to the right. We could do it on the left, but that's this period. Since we know this is the solution, let's apply a little bit of math here. We know the solution then is, for x, a cosine of square root of k over mt plus phi. And if we add a period to it, then it should be a cosine square root of k over m. And then we would have t plus capital T plus phi, right? That's really what you're saying, mathematically, right? How much time does it take to get back to that same position? And then fortunately, or maybe even unfortunately, we can do some trig and some trig identities, and we can figure out what the period is here. How much time does it take? I think the easiest thing to do is to realize that the time it takes has nothing to do with the amplitude. And so, if I come over here and I pull it 1 centimeter and let it go, it actually is going to take the same time as if I pulled it 10 centimeters and let it go. And that can be a little surprising, especially when you notice that the 10 centimeters is traveling a much larger distance. But what else did you notice? Yeah, it's much, much faster. And so one of the things you'll be asked to do in tomorrow's lab is to look at this and say, okay, does it take the same amount of time? And you'll try a small amplitude and you'll try a big amplitude and you'll begin to see, yes, so it seems to be the same. Maybe the best way to write this is to call this one variable. How about, I was going to call it A. Is that confusing if I call it A? Little a? Can I call it little a? All right, I'm going to call it little a. Because if you look closely at this can be written as cosine of, and if you write it as the square root of k over mt plus phi plus the square root of k over m capital T, then this can be thought of as A, and this can be thought of as B, right? And so, again, going through our mathematics, I then have cosine of A equaling cosine of A plus B. And so when is that true? Because that's the answer, right? When is it true that the position a time later is equal to the time before? And so if you can find a solution to that, you could tell me what the time does depend on. It clearly does not depend on amplitude. That was what we first noticed when the a's canceled off. And we can use our little trig identity. It's the same one we already started to discuss. What is the cosine of A plus B? Well, it's the cosine of A times cosine of B minus sine of A sine of B. Okay, so when is that true? Okay, so if that were to equal 1, and that were to equal 0, wouldn't it work? And the B is the part that has what I'm looking for. That's why I picked on the little b there. Because the A is a function of time. So this variable A has the whole continuous spectrum. And so at one moment in time it has one value, another moment in time it has another value. I can't choose that. But what I can choose, or what I can force, is this question. What does the T have to be? And it will work if cosine of the square root of k over mt equals a 1, while at the same time the sine of the square root of k over mt equals 0. And if both those conditions are met, yeah, and fortunately, when does this occur? This occurs, right, when the square root of k over mt equals, so when does it equal 1? Okay, I think we can make a whole series, 0, 2 pi, 4 pi, 6 pi, but in particular, one cycle, letting the time just be the first cycle, I would want this to be 2 pi, right? I don't want it to be 0. Of course it equals 0 when it got started. That wasn't the issue. And I don't want it to be 4 pi or 6 pi. That's the issue of after it keeps repeating itself. All right? So condition number 1 is that has to be true. And as you pointed out, that automatically matches condition number 2. So this is not added information. The sine function equals 0 every time the cosine function equals 1, right? So that is already met. There's no point in met. There's not an added condition on there. And so finally I get to what I wanted you to see, and that is the period. The time it takes for this little object to go back and forth then is 2 pi times the square root of m over k. Yay! Can I put a box around it? Because whether this was easy for you or hard for you, we did a lot. Right? We have shown something that for many of you might remember, I promised I would do this for you when you had Physics 102. I don't know if you remember, but we did our springs and our oscillations. It was also happened to be chapter 15 in 102. And I said, what is the period for a mass on the end of a spring? And I had a 2 pi, and it had a square root. And most semesters when I teach 102, students go, where did that come from? Where did the 2 pi come from? And unfortunately, those are the equation in 102 that I said, you know what, it takes some calculus. And you can see it here, right? Took some calculus. And it takes some trigonometry, so that's why we didn't do it in 102. But a day will come where I will prove it to you. And here we are. So I have proven it to you. Just like I said the same thing when we did mv squared over r. We did that in chapter 6 of Physics 121, if you remember. I gave it to you in Physics 102 and said we'd prove it when we learned a little calculus. And we did in chapter 6. And so likewise here, we learn the equation for the period depends upon the mass and the spring constant. It does not depend on the amplitude. So we already mentioned that. It does not depend on the amplitude. I'll show you it depends upon the mass. You might be able to see it. This one, unfortunately, can't handle too much weight on it, and the wheels rub. So I'm going to switch over to this one. These are my springs, if you will. It's rocking back and forth. And I would say the period's pretty small. This goes back and forth quite a few times, right? The amount of time for one cycle is not that long. This is pretty fast. But could I change the amount of time? How? Add mass, right? And so what if I make this little cart, which is about 300 grams, now 1,300 grams? Do you see a change? Do you see this number's bigger, and therefore the period's bigger? What if I make it 2,300 grams? And this might be too much for the machine. Let's see. What if I make it 3,300? We rubbing? Ah, if I get my... Oh. Barely. It's kind of twisting here a little bit. But you can see it has changed the period, and it's changed it dramatically. And the period does depend upon how much mass. It also depends on the spring constants. And let me come back to this one. This one doesn't work well by adding weights on there, but I can change its spring constant fairly easy. I'll prove this a little bit later. But if I take this spring and tighten it up by only using half of the spring, this one's not as easy. So I'll only do a little bit on that one. But that should have tightened up those two springs. That should have increased the spring constant. Can you tell a difference? Isn't the spring constant a little bit larger? And a little bit larger in the denominator means the period is a little bit smaller. And so sure enough, it goes back and forth with a different period. And so that is what the math has shown us. And of course what I'm trying to show you into the physics. I'll say it again. Write out the equation, come up with this. When you come up with this, you now have the solution. Once you have this solution, you can get everything else we're going to talk about. Right now, we've talked about the period, but we'll talk about its frequency, we'll talk about its kinetic energy, we'll talk about its potential energy, we'll talk about its total energy, its velocity, its acceleration. All of those are right here. And so the key to all these problems is right here. Write out the equation. See what the equation is. Once you got the equation, you also know what the solution is. Once you know the solution is, you can get the period, the frequency, the energy, the kinetic energy, the potential energy, the velocity, the acceleration, all these questions that your author, and position, let me not forget the obvious one. The position of it alone we can get. The author will say, how much time does it take for the object to move from position 5 to position -3? And so you can figure that out. Granted, it's going to have some math in there and some trig identities, but remember Appendix B will be very useful to you in this chapter. It's got all those trig identities buried inside of them, and so you want to go back and look at those. Now, your author does one little abbreviation, and so I should too. Your author does not continue to write the equation as the square root of k over m. Your author likes to use the symbol omega for that. It has its advantages, and so I will too. We'll talk more about that as the chapter goes along here. But writing it that way means, here's what I've found so far, that the equation for the position is given by this equation, where the omega is equal to the square root of k over m, which means the period is 2 pi over omega. The first one we talked about right here is the phase. The second one we talked about is its amplitude. And then finally, this last one we're discussing is probably best described as its angular frequency. Whoa, angular frequency. Well, what are those words? Well, again, let me come back to this. We got this word, period. What would frequency be? Good. Sounds like many of you remember from 102 that it's nice to talk about period or the frequency. They're so closely tied together that I think sometimes students confuse them. What is the frequency? Well, it's the number of cycles in 1 second. The symbol we're going to use is F, but please note that frequency and period are not quite the same thing. Did you catch that? What's the period? The time for 1 cycle. What's the frequency? How many cycles are in 1 second? They are the inverse, the reciprocals of each other. And so if you do know the period, you do know the frequency. And so I think period is the easiest one to understand. That's why I started with it. But once you know the period, you also know the frequency. So when I have something that swings back and forth like this, let me move it off to the side and see if I can get the period. 1, 1,000, 2, 1. Well, it wasn't quite 2 seconds, but let me call it 2 for the sake of discussion. I would say the period is 2 seconds. So what's the frequency? The reciprocal, half. It does a half a cycle in 1 second. Probably doesn't surprise you that the units for the period would be in seconds. The units for frequency then might be new to you. What would be the units here? Good. And we did see this in 102. It is called a hertz. It is an inverse of a second. Some of you, it sounded like, are even more familiar with inverse second. If you want to call it inverse second, fine, but hertz is at least a little more common in this country here, and so we call it hertz. And so I would say the frequency is a half a hertz. The period is 2 seconds. In fact, we can use that to extend out what we learned earlier. What we learned earlier is that the period is 2 pi over the square root of m over k, which means we get 1 over 2 pi times the square root of k over m, which means it is omega over 2 pi, right? And so there's a lot of ways of saying the same thing mathematically, but that's what we get, the frequency. The frequency is how many times does it go back and forth in 1 second. Okay. Again, those of you who had Physics 122, we dealt with frequency a lot in our electronics, and our electronics would go back and forth. And we had some high frequencies. I mean, we built those radios at the end, and we were using like 1.2 megahertz in our broadcast radio. And even your just regular radio that you might tune in when you're in your car, you know, that'll be 100 megahertz. And so these frequencies, depending on what it is, can go back and forth. Of course, we're going to be talking about mechanical things, so our frequencies won't be as high as 100 megahertz. But they can go back and forth quite a few times, 500 times a second, 1,000 times a second, 10,000 times a second. And so that's our frequency. But the reason I point that out is I'm hoping that that equation will help you with this word, angular frequency. Because when you write this here and here, and I'll rearrange it, so it says 2 pi times f is omega. This helps me get a better understanding of why we call omega the angular frequency. I'll start with frequency again. What is just what I'll call the normal, regular frequency? Well, the number of times it goes back and forth. So if you multiplied it by 2 pi, what are you saying? You're saying the number of 2 pi's it has, which is perfect if we had a wheel. Now, do we have a wheel? No. Okay, so don't forget that. We don't have a wheel. And I think that's what can throw people off. There's no wheel up here. There's nothing going in a circle, and yet we call it its angular frequency, and here's why. You can see it physically, but I think you can see it better mathematically because it works really nice mathematically. It simply is saying if the frequency is, say, 10, then the angular frequency is 20 pi. It is 10 times 2 pi. If I had a wheel that went around 10 times in 1 second, that means it would have gone those 10 cycles, each cycle being 2 pi, and so that's its angular frequency. How many radians does it rotate in that 1 second? So please don't confuse angular frequency with frequency. Notice that angular frequency shows up in the equation. Very useful mathematically, but not quite as useful physically. What's useful physically is the frequency. The frequency is something we can see, something we can count. We can take the spring, we can let it go. We can say it goes up and down 10 times every second. So when we go to put it in this equation to describe the motion of that spring, we would put in the angular frequency, not the frequency. Some people even prefer to write it. Now, your author does not write it this way. He says it makes it look more complicated, and it does make it look more mathematically complicated, but I like it. I think it makes it look more physical. It tells me right away that is the frequency. That is the number 10. And then 10 times 2 pi would be its angular frequency. So, again, don't miss the idea of frequency versus angular frequency. Okay? And I should show you on a graph. On a graph where we are plotting position versus time. If omega is small versus omega That is big. What would these look like on the graph? What would they look like physically? What are we trying to say here in this solution? What would small omega mean? Right, it means the frequency is small. It would say it's taking a long time before it gets to one cycle. You can see it here, the period. Yeah, well, maybe I should write it also this way. The period, which would be 2 pi over omega. You have a small omega. You have a large period. And so a small omega takes a long time to complete one cycle. Its frequency is low. Whereas a big omega means what? That does not take much time to complete a cycle. And that's what this first lecture is all about. Do you understand these three things? Do you understand where this equation comes from? And did you catch my warning that that's how you do the homework, right? Write out the equation of motion and you will get a second order differential equation that looks a lot like this. The solution to this is this. And this will tell us everything we need to know. Everything we do for the rest of the chapter, we'll be studying these parameters. And there's a phase, there's an angular frequency, there's an amplitude. And of course, these things are related to other things. Angular frequency is related to frequency, which is related to the period. Okay? And so that's these three biggies and how they tie together. Maybe an example in the closing minutes would be good. Now that you saw what I would call the general principle, and I'll say it again, that general principle. Start off, Newton's second law, write out the equations, you will get a second order differential equation. That will be the solution. That will tell you everything you need to know. It'll tell you the amplitude, it will tell you the frequency, it will tell you the period, it will tell you the velocity, it will tell you the acceleration, it will tell you the kinetic energy, it will tell you the potential energy, it will tell you the total energy, and we haven't done all those yet. Those are coming up on Thursday. But everything we need to know then is buried right in there. So that's why I said at the beginning of this lecture, no new physics. Just applying the physics and the math we already know. So, as a second example, what if I had two springs? Let's just take this one step harder. Let's actually solve this one. The one I did for you only had one spring, right? But this one has, well, I'll leave it this way, the few minutes we have, instead of trying to untangle that crazy thing. Well, this one will be easy. I'll do this one. Here. I lied, it wasn't easy. Okay. Actually, maybe I should. Nah, I'll leave that there. Okay. But let's just take the two springs and let it go. Could you tell me the equation of motion for this? And thereby, could you tell me the frequency, the period, the angular frequency, the velocity, the acceleration, the kinetic energy, the potential energy, the total energy? I already said velocity. But all the other parameters we're going to ask? I bet you could, and here's the idea. Start off, keep losing that wet one, where'd it go? Start off by writing the free body diagram, or drawing the free body diagram. And so in this case, I would say, all right, here's what's different. What's different in this problem compared to the one we just worked on for the last hour and 20 minutes is this. That if I hook a spring here, call that spring number 1, and over here I have spring number 2. When I go to add up all the forces in the x direction, what do I get? Well, why don't we call the center x equals to 0 for a moment. Okay. So let's say it was over here to the right. how much force would I get from this spring? Minus K1x, right? But wouldn't I also get a force from this spring? How much? Now, would it be a positive K2x?
Positive, yeah.
Negative K2x?
You get a negative here, you get a positive there.
Okay, so can we at least agree it would be a K2x? Okay, so we're not much in agreement. But I hear some of you saying positive and some of you saying negative. Well, let's see. If I move this way, the position is positive. Right? Which way is the force? Negative. Oh, so someone negative there? Oh, what about when it's over here? So when it's over here, the x would be a negative number. So the force should be positive. And isn't that what I get when I have the negative? And so I think this might be a little hard at first. In fact, this is where the hard part comes in all the homework problems. Write out the equation. I guarantee you will get an equation that looks a lot like this. It may take you a little bit of effort to write it out, but once you do, you will get that equation. When you get that equation, you will get this solution. When you get this solution, you know the period, the frequency, the energy, the kinetic energy, the potential energy, the acceleration, the velocity. Okay, and I can't say that enough, but it is a negative. I know it's very tempting to put a positive here, and since we're a little bit low on time, I'm going to leave that at that. I'll let you keep thinking about that, but we should get a negative for each of those. Those are the two forces. There are no other forces, so that's the next hardest one. So this is the next level of problem I can do. What would it equal? Okay, MA, and of course, as you said, that would be the second derivative with respect to x. Could we simplify it so that it looks maybe something like this? I think we could. Couldn't we write this as a negative K1 plus K2 times x over m equals the second derivative? Doesn't that look a lot like this? And that's the point I'm trying to illustrate, is that the problems we're about to do, the problems you're going to see in the homework are going to get more complicated. They're going to have 2 springs, 4 springs, 7 springs, a zillion springs. They're going to be hooked on either side. They're going to be hooked on the same side. They're going to be hooked in series. They're going to have objects that roll, some with friction, some without friction. You're going to have torques. You're going to have moment of inertia. But I can guarantee this, that after applied Newton's second law, you will get an equation. That's where you're heading for. Head for that equation, because when you get there, what does that tell me right there? Everything I need to know. Right? I'm done. That is the solution. I know that x as a function of time equals some amplitude, depends how far I pull it, times cosine of square root of k1 plus k2 over m times t plus phi. There's the equation for the solution. If somebody asked me to write out the equation of where that object is, I have just done it. If somebody were to ask me what's the period, I would say the period is 2 pi times the square root of k1 plus k2 over m. If somebody would ask me what the frequency is, it would be 1 over 2 pi times the square root of m over k1 plus k2. If somebody were to ask me what the angular frequency is, I would say it is the square root of m over k1 plus k2. If somebody were to ask me what the velocity is, and maybe I shouldn't do that one quite yet because we haven't got that far, I would take the derivative of the position to get its velocity. If somebody were to ask me what the acceleration is, I would take the derivative twice of the position to get it. If somebody would ask me what the kinetic energy is, I would have it 1/2 times the mass times the velocity, which I got the velocity by taking the derivative once. If somebody would ask me the potential energy, I would say it is 1/2 kx squared, where x is that thing, right? Everything you can ask me, I know. So I'll say it again. What's the point? I guess I didn't mean that quite that general. Although it reminds me of a joke I played with my kids. They were about, they probably figured it out when they were about 9 or 10. But they were starting when they were really young, about 4. I told them, your grandpa and I know everything. And he would always challenge, no you don't. And he goes, yeah. And he'd ask me something like, oh yeah, what is the capital of Spain? S. Okay, that was easy. Okay. What is the population of Spain? Ah, your grandpa knows that one. Oh. And that went on for about 4 years before he finally figured out. Grandpa doesn't really know those. You just say that when you don't know it, huh? So, anyways, I didn't mean that. But I'm sorry, there were a bunch of questions, yeah. And we got it. Well, we have 10:05, we're done, right?
For your period there, why is it K1 plus K2 over M? Wouldn't it be M over K1 plus K2?
Oh, I might have went too fast. Yeah, the period. Yes, you are absolutely
Same for angular frequency then?
right. Did I get these backwards? Yes, that should be K over M, right? Yeah, backwards. Sorry. Good, and that means you saw the pattern. And basically, all I did was say this is the equivalent K, right? Everywhere you see a K, replace it with K1 plus K2. Oh, and then the frequency was off also. Well, maybe I'll stop there because I could add to this. What if I had the springs on the same side? What if they were hooked in series? What if they were hooked vertically and had the force of gravity? Well, that'll be a good place to do tomorrow. All right, so we'll stop there, and I will see you Thursday. It's not tomorrow. All right.
Thank you.
The final for the class is 10:30. Is it included also because my 200 finals like 5 minutes?